So what do I mean when I say cut and carve demolition? What exactly is it? Well, cut and carve involves a detailed and technical process in which the structure of a building is re-engineered to enable proposed changes or sometimes to correct some defects. And we're not completely demolishing it. It's structurally modifying a building to turn it into something that's desired by the client in the end, but be that a new building layout or installing new structural elements or removing structural elements. Here we can see as an example, a layout with the demolition works highlighted in red there, and that's on a job in West London at the Gramophone Works. And you can see that some of the floors are going to be removed, the facade's going to be removed, load-bearing walls, and some parts are also remaining in there as well. Interestingly on this one, the scope included the removing of an area of the slab completely. That's just one of the examples there. There's two shown there. That's shown in red. And then the area shown in blue is where they were just breaking back the slab and leaving the rebar sticking out so we could tie the new structure in. This isn't always required, but sometimes it is. But all this work must be done whilst keeping the rest of the building standing up. Sometimes we end up with a structure that looks a little bit like Swiss cheese with lots of holes in it. And then we go in and build new things in the structure. And then, hey presto, we have a new structure as desired. A good example here is Centrepoint Tower in London. On the left, we've got the demolition scope, and on the right is the structure of what went on the right is what went back in. This required significant and well-coordinated temporary works to achieve this right at the top of the tower. So this is 34 floors above Oxford Street and Tottenham Court Road. And this was to stabilize the structure that remained before the reconstruction of the subsequent and removal of the temporary works. Facade retention can be part of cut and carve as the structure behind the facade is removed, leaving some of the structure back. It's not typically what we mean by cut and carve. However, facades are often maintained on these jobs, which often requires some form of support. And here we can see a couple of examples of full facade retention that we've done. Here's a really good example, so I'll just make that a bit bigger. So this is Birmingham New Street Railway Station redevelopment, and this is the top level of the building. The new bubble-like roof over the top that you'll see now, and that forms the new roof to the cathedral-like space that's at the concourse level in the station today. Before, the station had lots of RC structure above it, and it was quite oppressive with low ceilings, but this work involved the structure being removed within its footprint of the roof. And it's a good example because what we're doing here is removing specific parts of the structure whilst keeping the rest of the structure intact, as well as keeping the building in operation, because the concourse level, which is directly below where these operations were, is kept live throughout. In this case, we were able to run some quite heavy plant on the structure. So working on the lower retail level, you can see a 25-ton JCB demolition rig, which was custom made from various parts of different excavator specs to run specifically for this job. That was called the Mega Muncher. And then where that, you can also see the Brock's gone now, it's done its job, but that was kind of, the Brock was sequentially removing some of the slabs as part of this work. And then following this part of the phase, the floor that Mega Muncher was sat on, that was removed as well. And that creates that big open air. Another good example here is Waterloo International Terminal, which is part of the Waterloo Railway Station. The red area shown on the drawings is the area that's is going to be demolished, and then the rest is being kept, all whilst working in a live station and directly over the Bakerloo ticket hall. So removing the structure and elements that were no longer required due to the change in use to enable a new retail space to be constructed just in this area. Careful demolition methods with significant amount of temporary works was required to ensure that the remaining structure was kept stable throughout while those key structural elements were removed and then subsequently replaced. So for example, on the right, top right there, you can see that there's it was a pedestrian or a walkway down from the platform, and that was going to be removed because they didn't need that walkway anymore. It used to go onto a little bridge, and then a new flat slab could be cast there to allow that new space for the new purpose of that structure. So as a little recap, it includes substantial elements of the structure being retained for further use in the future. And you have to keep the structure stable, which may include stabilizing floors, walls, load-bearing walls and columns. And we need to consider how the structure will be kept stable, which will often include a substantial amount of temporary works. It's often going to require controlled demolition strategies, such as cut and lift, top-down demolition, careful dismantling, using methods such as diamond drilling or concrete cutting, bursting, breaking, and small-scale pulverizing, all really depending on the application of what we're trying to achieve. It's unlikely that a high reach machine is used for this kind of cut and carve job, though it's not impossible. It is already dependent on the structure and the situation, because it depends on how much structure is being taken out. But generally, you're looking at a very controlled demolition method, taking little bits out at a time. So why do we end up doing cut and carve demo? A common reason why we often end up doing cut and carve demolition is due to planning restraints, really. It's a lot easier to obtain planning permission for a project that is modifying the structure and keeping the majority of what's already there, as opposed to knocking the whole thing down and starting again. It's looked on a little more sympathetically by the planning authority, usually. If the structure has been assessed and there is some redundancy in it, then a structural engineer may well say, well, let's put another floor on top to increase the floor area of a building. It could be a lightweight steel structure or CLT floor above the existing building. This could be perhaps 3 floors, up to 3 floors or so, and then changing the cores, moving the lift shaft arrangements to better suit the new proposed use, i.e. a new open plan office space, for example. It could be due to the change in use of the structure, which with current work culture trends or moving towards more home working, then office space may well turn into residential, which may include mucking about with the structural layout. If the facade or the structure is of heritage or historical importance, then you're not going to get away with demolishing it. So you're going to have to keep a little bit of it and work around it, depending on the particular planning constraints. And the other one, which is becoming increasingly more prominent, is how your carbon footprint is affected by the proposed development. If you can keep a part of the structure and reuse it, then it may well reduce the amount of carbon spent on that demolition, but also keeps the embodied carbon within the structure too. So as opposed to knocking the whole building down and starting again from scratch. So what makes it different? Well, there are a few things that I've identified here that make it a little bit different and sets it apart from other demolition strategies. Deflection becomes more important. If we are demolishing large parts of the structure, then the assessment of the settlement and timeline of movement to tie the structure back in is very important. This includes the progressive settlement that you may get on a cut line propping if you've got lots of floors of it, because you don't want to end up with a wibbly wobbly floor when you come to recast your new floors and they're at the wrong level. So that's important to take into account. Taking into consideration serviceability. Usually serviceability is much lower down the priority list for demolition, as we're interested normally in maintaining structural stability only. So for example, on a building being mechanically demolished with a high reach operating on the ground, we don't need to ensure that the floors don't deflect too much so they're uncomfortable to walk on for human beings. So we don't really care as long as it doesn't fall down. That's great. Again, superficial cracking, not really an issue if the whole lot is going to be demolished. Load history, that's a phenomenon which must be considered, and I'll go through that a little bit more detail shortly. Stability, that tends to be an issue, as typically these schemes involve moving the primary lateral stability structures such as shear walls and lift cores. Therefore, significant temporary works may well be required to ensure that the structure remains stable during this re-engineering works. And on these schemes, the core structure often goes first, as opposed to traditional methodology of demolition, like a mechanical demolition with a high reach, where you're demolishing the whole structure and you typically work towards the core or the stability structure to keep the thing stable. And another one is quite important. So that's how the structure is going to be left for the follow-on contractor. On traditional demolition job, where the whole thing is removed, you've got a blank slate to work with. However, with cut and carve, the handover has much more complex interface. Usually the sticking point is the temporary works that remains, that's left in place. That has to be designed so it's constructible for the follow-on contractor, so they can reasonably carry out the required works if the temporary work's still in place. So it requires, there's quite a complex interface between the two there. So let's have a look at deflection. If we are propping over a series of floors on a cut line, say could be 6 or 7 floors, then the cumulative deflection, that is the deflection added up across all of the propping going up, that may well become quite significant at the top. It may look acceptable on a local basis if we just consider one floor and one lot of propping, but it's going to be important to look at the bigger picture to ensure that we're not exceeding the structure's tolerance. So this is also true for cut line propping to ensure that slabs are adequately supported and creating a new pin end to a slab. If we've got our cut line where it used to be continuous, we're not going to overload that slab. And in the case of the slab, if it's being retained and then it's experiencing loadings that's never seen before, and hence it may lead to cracking or micro cracking. And if we look at the comparison of these that I've shown at the bottom here, so this is on the left is the existing condition, and if we've got a cut line on the right hand side, well in the middle of the beam on the right hand side, and we're putting a prop in place, then the bending moment diagram changes for that slab or beam, which needs to be accounted for. Otherwise we could get some cracking or potentially a structural failure may occur. And we've got similar issues with both beams and columns as well. Essentially with deflection, you can get into the issue of the final stages of the project where you come to recast your floors and you find that parts of the structure have dropped 20-30 mil or so, which is extremely awkward to fix and to explain as well to your client. And this needs to be thought out much earlier in the project to ensure that it doesn't become an issue when it comes to handing over the job to the follow-on contractor. And here we've got an example of a modification of propping on a job that we worked on, which was over 6 stories of propping. And the issue was this cumulative deflection in the propping. So we looked at a scheme without jacking, and the deflection was around about 45 millimeters, which was outside the scope of requirements for the level floors. But with jacking, we could reduce that down to 17 millimeters, which was within the allowance of the specification. And as you can see here, the proposal, it's not straightforward. And it's important to get some proper thought into the constructability of the structure and getting the temporary works right to ensure we've got a successful outcome. With complete demolition of a structure, we're not really interested in serviceability conditions, like I said, and we're looking to ensure that there's no failure of the structure on that part, whereas that's not the case when we're retaining parts of the structure. So as an example, I'm going to talk about 20 St James Street in London, which was a cut and carve project where the cores were being removed and strategic elements were being retained. So removing parts of the structure whilst not exceeding the serviceability conditions of the structure is really important for a cut and carve job. And by serviceability conditions, we are principally looking at deflection and cracking. And we're not talking about the kind of cracks, the large cracks that you see on the structure. We're talking about pushing the structure to an extent that leads to micro cracking, which in the long term can lead to corrosion of reinforced concrete, which affects the overall design life of the structure. Also considering the change in load path as well of a structure, which takes some careful consideration. So with cut and carve, it's important that there's a really good understanding of how the structure behaves, what it's made of, the construction details, the rebar grade, and the layout of reinforcement. This is information that is taken from archive drawings and site investigation, but it becomes much more important for both the temporary works engineer and the permanent works designer when you need to keep a part of that structure, which is the whole idea of cut and carve. So in these photos that I'm showing, we're just demonstrating some of the temporary works that are required potentially for a cut and carve. So we've got some cut line propping here, the retained structures. We had some sway stability bracing shown in the previous pictures, and on this one, this structure here was the storage room for a super duper high-end tobacco shop that had lots of very expensive cigars kept in a temperature controlled room, shown here sticking out into a live demolition zone. So sometimes we're working with very sensitive structures. It could be switch rooms for substations and things like that, when we're carrying out demolition of this cut and carve. So it can require some very careful methods of demolition. And also you can see there's some quite significant temporary works required on these projects, because we're taking bits out, keeping bits in. So therefore we need to make sure that they're sufficiently supported. And here we can see some core drilling works, which is kind of making the Swiss cheese effect that I mentioned earlier. And that chap on the right doesn't seem too happy about that work either. But I just wanted to show you that, you know, these can be quite a slow process. It's not a case of getting a big machine, a big hammer and taking the structure out. Sometimes it can be quite careful demolition methodology. So serviceability is also very important when it comes to pre-stressed structures. And here we've got a tipper wagon traveling over some pre-stressed bridge beams as it's loaded to remove some cut sections from a cut and carve job. We had the ULS capacity, so that's the ultimate limit state capacity to cope with the loadings from this wagon, which meant that if we ran over it with the wagon, then the beams and the slab wouldn't collapse. But we didn't have the serviceability capacity, so which meant that we could potentially get some cracking. So we had to prop it, as shown here, and that's case in point really. Because we were keeping the floor, we had to make sure that we preserved the design life of the beams, whereas if they were being demolished, they wouldn't have failed, so we wouldn't have bothered putting the propping in at all. And then we can see that in use. That's the propping of the slab is beneath there, so you can't see that. But this is the wagon being loaded out by those bespoke crane and crane rail system that we designed. This is a Birmingham New Street project and phase 1 removal of the NCP car park, which won the award. I think it's contract of the year or something for World Demolition Summit off the top of my head. But it was a super duper project. That's good. Okay, now load history. And this is an issue that we come across often when a scheme crosses our desk, and it's seems that people find it a little bit tricky to grasp this concept. So I wanted to discuss it here today. So we've got this structure, and this is the demolition scope. We've got the slab at the top being removed, the lower floors being removed as well, and we're taking a little bit of the column, which we're going to end up tying into. But what seems to be missed is that if this broken out part is removed, then all of the dead load of the structure above goes through the remaining structure here. It's got to, because that's the only part left. So now this remaining section is taking all of the stress that results from taking that dead load from above, okay? When the new concrete section is cast back in and the new green part is put in there, that's shown, that's only ever going to pick up any live load or any new dead load that's applied to the column. The existing dead load is still taken by the grey part as the stresses are essentially locked in there. This becomes very important when assessing that remaining column. The stresses are being applied from all of the dead load and all of the live load. They cannot be shared evenly across the whole column section, as some of the column is still taking that higher stress load from the dead load previously. Therefore, there runs a little risk of, well, not a little risk, it could be quite a large risk of underestimating the magnitude of stress in that column, which may lead to failure, be that serviceability or ultimate failure. The only thing you can do, that is if you need to share that load evenly across the whole column, is jack up the whole structure, and then this essentially unloads the column completely, and then cast in the green area, and then release the loads from the jack, and then that will put the loadings back in shared evenly across there. Similarly, if we had a steel column that's being strengthened, then adding bits of steel to it while it's loaded, that's not going to cut the mustard, I'm afraid. Jacking would be required if the load needs to be shared into the whole column. Otherwise, the existing column will be taking its existing load plus its fair share of any new load that's going to be put on it. This is a fundamental engineering phenomenon, I guess. which we see mishandled in schemes more often than we'd like, but it's important to get that understanding down. And now I'm going to lead on to stability, and for that I'm going to pass on to my colleague James, who's going to take us through a detailed case study looking at stability in structures. So I'll stop sharing and over to you, James.
Yeah, I will just share my screen now. And can we all see that? Can I get a thumbs up, Josh?
Thumbs up from me.
Sorry.
It's all good, mate.
Very good. So yeah, I'm going to be talking about the case Colston Hall, which is a case study that, the Bristol Beacon, I should call it now. It's been renamed over the course of the project. I did discuss this in the Christmas seminar, in the Christmas presentation, but I think it's worthy of a bit more, and I've gone into a lot more detail today to discuss that job. So the Bristol Beacon project is the full redevelopment of the theatre to bring it up to modern standards. It was originally built in 1864, and the Great Hall burnt down in 1898. It was then rebuilt in 1900 and refitted again in 1936, and then gutted by another fire in 1945. Its most recent refurbishment was in 1951, and essentially the legacy of all of the previous works and refits need to be considered in our new redevelopment works to make sure that we are considering things like load history, like Josh suggested before, as best that we can. So our client for this project was initially DSM, who undertook the demolition works, and then after them became Wilmot Dixon, who are the main contractor on site. And we've continued working on items of temporary works for both these clients, essentially because we had a very good understanding of the structure, and because I think we'd impressed in the first phase of the work, shall we say. We've completed over 70 jobs on this scheme to date, and I'm going to be talking through some of the most challenging ones now, which are the arch tying, the facade retention schemes, and the pier restraint propping, and the sequencing that we had to devise to get around things like load history, like Josh has just discussed. So to go to show a section through the structure, the Great Hall is the hall on the left-hand side, that has 2 levels of arches beneath, or what's the word? The arches.
Vaults.
Vaults, he's got it. Yes, there's 2 levels of vaults beneath, sorry. And on the right-hand side, we've got a secondary hall, which is slightly smaller. On top of the vaults, we undertook several different plant justifications for small cranes, moops, and other demolition equipment. And as you can see, in between the 2 halls and beneath the secondary hall, there is a lot of arches that we've had to assess, and we've undertaken stability assessment of to tie the arches to enable demolition works to proceed. The highlighted section on the the highlighted bit in blue in the middle is the section I'm going to talk about now. So this scheme is to allow for the infill in the arch to be removed and for the new opening to be installed, as shown just to the right of it. It was interesting to see that the pier above didn't align with the pier below, meaning that there was a slight eccentric force into the pier in addition to the arch thrust. So we developed a simple solution to tie the arch by chasing angles into the pier and clamping these through the pier, and then tying these back around to the adjacent pier, which you can see in the details on the right hand side. So following this, the scheme was revised, the permanent work scopes were revised to include a new arch instead of a box frame. So we provided sequencing to enable the installation of the new arch, which is shown there. So this image shows an overview of the Great Hall. The outer walls were roughly 16 meters high, were rubble-filled masonry walls. The photo to the top right shows what one of those walls looked like if you were to saw cut it, and what we mean by rubble-filled walls. So if I work my way around the structure, if you can see my mouse, this is the 16-meter rubble-filled walls. We've got a large pier located here, and then you've got two walls that run parallel to one another, working along your way here. We've then got the organ housing to the rear of the building, and then we've got another two walls here that are parallel to one another, a large pier, and then another rubble-filled wall along this side. It's worth noting that the top section of this rubble-filled wall was rebuilt following one of the fires, so the piers don't align with the piers on the opposite side of the structure. They align with the new, or the old but newer roof trusses. And then this gable end here, that extends around 12 meters above the party wall, and also required support. So I've overlaid our facade retention designs and split them into three sections that I'll discuss shortly. The gable end wall on the left hand side, the central frame in the middle, and the stage end towards the right hand side. These schemes are, unlike most ordinary facade retention systems, as a typical facade retention system would be supporting a typical facade which is supported level to level. This is no ordinary facade in that way, because it was designed to span significantly more than one level. So our system was devised specifically to suit this structure to minimize the amount of temporary works as much as possible. And our initial analysis was of the existing structure to determine how best to support it. And we found that two levels of wailers was the optimum for the majority of this facade. So here we've got a section through the Great Hall in the as demolished condition. Here is our central facade system overlaid, and here is the permanent work structure overlaid. We used these models to clash detect in our design around both the permanent works and the existing structure. So firstly, I'm going to discuss this central section. So the frame was designed to work essentially as a large portal frame and transfer the forces down to the base of the wall. Using this approach, we removed the need for cantlage and used relatively lightweight steel sections because we had quite a big depth at the top, and we could go for quite wide frames. We doweled into the outer walls to resist the uplift, and we founded the steel columns on the piers beneath in the vaults to align with the piers of the vaults. We also detailed the system to be easy to assemble and detailed it as pods. So the two ends were fabricated sections, and all of the bracing between them was just lightweight members that could be bolted together easily on site. So it sped up the installation process. The gable end system was designed to transfer load back down to the existing piers. So we detailed this system to support the wall at two levels and designed trusses to transfer the load from these levels back to vertical trusses. So you can see there's a horizontal truss here and here, and they transferred the lateral forces down to these vertical trusses, which you can see here, which are clamped around these piers, which are lower down. Here's another view of that facade retention system. Due to the nature of the structure in this area, the client provided us with a point cloud of the as-built temporary works, so that we could detect clashes with the permanent works. We then reviewed these in the model and worked closely with the site team to come up with a sequence to ensure that the system could be installed around the temporary work system. So here we can see that the installation of the new roof was just starting to commence, with the gable end frame to the rear and the central frame in the foreground in the photo. The stage end system transfers a proportion of the lateral forces down to the rear wall, which you can see here through ties. So there's diagonal bracing here that transfer the load down to this level, and then the shear walls at a lower level to transfer that further down. The truss here in the foreground of this image transfers the load back to these large piers that I've drawn in here, and you can see photos of these as in built on the left and right hand side. And as I'm sure you can imagine, it was complex to analyze, but it was very rewarding to see this installed on site. Here we can see an aerial view of the facade retention installed, with the roof installation in progress. For the whole of the facade scheme, we had the same engineer, which in this case was me, attend site, liaise with the client, complete the design calculations and the design drawings and the fabrication drawings. And a lot of companies split these roles between from the drawing to the design between different people, and essentially our approach has minimized the risk of something being missed, and for a scheme like that's quite a critical item. And I think that's perhaps why we were kept on in the job, because of our for the next contractor, because of our just in-depth knowledge of this job. And I think the next phase I'm going to discuss, we're going to emphasize that point. So either side of the stage area, the existing piers were to be stripped back whilst the facade retention was essentially under load. We provided designs to stabilize each pier in each direction to enable the demolition works as highlighted on these drawings, as on these annotated sketches. Which I'm going to run through these designs now, starting with towards the stage direction / away from the stage direction, left to right as you are looking towards the stage. So I think it's piers 1 and 2 I'm going to look at first. So piers 1 and 2 are the ones that I highlighted earlier with the red hatching, which I'm going to show you. So the red here is piers 1 and 2. So in order to remove the brickwork that tied these piers, which are essentially 2 piers in themselves, we devised this temporary propping and sequencing. So the temporary propping is on the left, and on the right we've got a temporary a sequencing to install this and enable the demolition of this masonry that tied the 2 piers. So we've got 1, install the upper temporary bracing and notch the bottom of that, notch the top of the masonry infill. 2, install the bottom half of the lower bracing frame. 3, complete the demolition in a typewriter fashion, and then 4, which was to install the remainder of the temporary bracing. And stage 5 would be to install the permanent works, which were on the blue hatched sections on the staging. So onto pier 3, which was the rear left pier as you're looking towards the stage. So the image on the left shows a plan of the area with the walls to be removed highlighted in blue, in the blue hatch. And we devised a propping scheme to restrain this pier, which was essentially a trussed PFC that doweled through the structure. We can see the photos of that installed on the right hand side. The system was initially designed as an R&D system with super slims, but the client requested this to be changed because of the amount of time it was going to be on site. Due to you'll notice that there's more dowels through the structure at the bottom, and that was to resist the uplift forces. So pier 4, which is the one that was on the rear right hand side, the stability, the system stabilized that pier by transferring the forces, which you see I've put the diagram on. So we're looking at this direction at the minute. So it transferred that force back to here and then up to this wall through a shear key, where we tiled that into the wall. And the lateral, so the vertical or up and down force on this diagram is going through that wall, and the left to right force is going through this wall, which is the other component from that diagonal. And you can see the isometric view of it here, and you can see the elevation of it on the bottom left hand side, showing the 2 levels of propping located here, and further up you can see these 2 blue lines. So they're the 2 lines of the whaler from our facade retention, just to kind of give you context. On the right hand side, there's a couple of photos of the as installed temporary works. Unfortunately, it's not the clearest, but that is those propping. So this photo at the top is me stood here looking this way towards those props, and this is me stood in the stage area, essentially looking up to looking up at that props. So now I'm going to talk about the pier stability along the length of the building, which is, I'd say, the most complex item on this job. The pier stability, essentially both piers were going to be saw cut and trimmed to thinner than the initial scenario. So there was going to be potentially higher stresses in these piers than initially. And there's a new permanent works system to pick that up. But in order to get that in, we had to devise a sequence to temporarily deal with that. And obviously this had to consider load history. So phase 1, this is essentially a summary of the existing propping schemes that would have to react or interact with these piers. So the whalers from the facade retention are shown at the top, and the bracing to the rear pier is also installed, which you can see here, the PFC bracing system. There's another system here or at the end of this section of masonry, because this existing wall is about to be demolished. So those have all got to interact with the removal of this section of pier, or the section of wall, sorry. So phase 2, we are installing a raking prop to the left hand side and a horizontal strut to tie the 2 piers together. And we've installed a small needling scheme within the opening, which is highlighted as D2. So phase 3, we commenced the demolition of the wall as shown, and this had to be completed in a very careful, methodical manner. Phase 4, we commenced the installation of a portion of the new permanent works with the ground beam and a section of the right-hand side columns being installed. We then introduced a raking strut to support the right-hand side here and the new column, which was then tied here. So phase 5, we can now remove the horizontal strut, allowing us to install more of the permanent works and so a couple of heavy-duty Megashore props. This prop was then jacked to take up a portion of the load. Again, remembering or considering load history to try and relieve the stresses in the current pier. We can now that we've picked up those loads, we can now essentially strip the pier back or do the saw cut along that line. Now we again, this had to be a very careful operation, and we detailed a stitch drilling to the top of the pier, or to the top of the section to be removed, and then at this point we advised the client of a hold point so that we could view the condition of that rubble-filled wall to make sure that we weren't going to be undermining any support condition by removing it in this way. That all turned out to be okay, and then we continued with that demolition. So phase 7, now the demolition is complete and we can install the remaining permanent work structure. We then amended our tie to clamp the permanent works columns and could remove the Megashore props. Phase 8, we installed the new permanent works crossbeam, allowing us to remove the internal raking prop. And phase 9 is the condition at the end of our works, and essentially the point at which the new concrete slabs and diaphragm action from the concrete slabs had to be in before any more temporary works could be removed. And I'm going to share some photos of the system kind of halfway through being used, I suppose. So you can see on the photo on the left, that's the left-hand side as you're looking at the stage. You can see the needling is in, and that section of wall that was previously here has been removed, and the raking, horizontal struts are in and the raking props are down. Exactly the same for the right-hand side of the stage, and this photos me step back to kind of give context to the whole thing. It's a very complicated job. On the left-hand side, we've got a photo of the phasing slightly further on. You see there's a couple of Megashore props now here, which are taking the load from above. And you can see this photo here shows the jacking arrangement at the bottom of Megashores. And the 3D isometric is from the drawing that we produced to produce the sequence drawings. It's overlaid in this drawing is essentially all of the propping that we designed and all of the permanent work, so it's kind of all over one another, but I thought it was useful to show that all the different phases together. And in reality, I don't think we've actually detailed a great deal of props. I think it's quite a neat system. One of the challenges was this clamp detail, which is here. So I've made that slightly larger just to explain what's going on there. So we had to clamp around the pier as it was. We had to clamp around a portion of the pier to enable that strip to be removed. And we also had to clamp around the pier with the new, around the new columns. So the system had to be quite flexible, and we designed the system to deal with this. And you'll note here, this is the same detail that we used to tie the arch, because it was proven to be very successful, and yeah, it was a nice and neat detail. I think this project really shows how complex the temporary works and maintaining stability of a complicated structure can get, and how the attention to detail is key on such on ensuring such a project is successful. I'm now going to pass you back to Josh to summarise.
Thanks, James. Yeah, just reiterate what James said. It just goes to show, I think that's the case in point really of how complex something can be, and getting the understanding of the structure is absolutely essential when we're thinking of things like load history phenomenon, which can easily catch us out as engineers. And so the projects that we've highlighted today really illustrate to me how important it is to get the correct methodology in place first, which is absolutely critical for these complex demolition projects that we work on. The right methodology changes from job to job and from client to client, really. So that's why it's a good trusted relationship between the project team leads to good projects, good being, in this case, safe and successful projects delivered on time. We work with many of our clients early on, even at tender stage, to provide that engineering input, which assists in choosing that right method and getting that right sequence. As you can see from James's detailed case study, that sequences can be quite convoluted, but absolutely necessary for a successful job. So as a little summary of what we've looked at today and what Cut and Carve is, we've discussed what it is and why it generally happens with some case studies too. But as an inspiring mentor used to say to me, so what? So what are we going to do with all this knowledge? Well, with Cut and Carve demo, that we need to consider serviceability conditions a little bit more. We need to consider load history and other phenomenon associated with structurally modifying a building. Deflection becomes far more important. Stability is more likely to be an issue, resulting in potentially more temporary works. And also how the follow-on contractor is able to complete the scheme. This is potentially dangerous as a handover point, as there should be a very robust and formal handover with as-built of temporary works installed and proposed sequencing as necessary. There's not always a demolition specification that highlights allowable tolerances for slab deflection, for example, so it's extremely important and definitely one to plan out way ahead so we don't get caught out. So if you want to know more, there is plenty of information out there. James, if you want to nudge the slide on to the next one, please.
Yep.
There's loads of stuff out there. Temporary Works Forum is a really good place to start, with lots of information and discussions and chats and some guidance on there. There's BS 5975, which is the Temporary Works British standard, covers procedural control of temporary works as well as permissible stress design. There's the National Federation of Demolition Contractors, NFDC. They've got a guide on temporary works. And there's also the IDE, Institute of Demolition Engineers, and also Safe by Design, early focus on constructability and temporary works, which I've noted there. After all, knowledge is power. So the more we know, the more we can de-risk our complex demolition projects, and enabling you to make the right decisions at the right time. And yeah, I think it's time for some questions. If you nudge onto the next slide, we've got an excerpt there of our YouTube channel, which please subscribe to that. And there's loads of hours of content, demolition, temporary works, all sorts of fun, juicy stuff on there. Yeah, I've been Josh Martin, Director at Andon, and James Dunlop. And yeah, we'll take a little break now and pass over to